Alright, hello everyone. Today we're going to continue our talk of rotation, and it's going to be a fairly easy talk because we've spent this first part of the school year learning all this physics, and now it's going to be a lot easier on us because all we have to do is apply it in a rotational context now, something that's spinning around. So what I'm going to do is I'm going to talk about the variables that we've been using and that we've become familiar with, and then I'm going to translate over into rotational. Okay, so everything that we've been doing so far has been pretty much linear. Everything has been going in straight lines. So I'm going to call one of them linear land. Okay, and then I'm going to call the other side rotational. We have linear land and we have rotational land. So we have to start with the oldest variable that we have, and whenever we start these topics, it seems like we always start with our good friend time. Time is going to be the same in both linear land and rotational land. Time does not spin, it just ticks away. So time and time is going to be the same. The next variable that we looked at was, in fact, distance, and we represent that with d, x, y, many other different ones, but today we'll stick with d. When we're translating distance over into rotational land, we're going to call that theta. In linear land, distance was just a distance from here to there. That's all the distance was. In rotational land, something is going to start at one point and it's going to sweep out an angle of theta. Okay? So instead of just a linear distance, we now have a rotational distance given by an angle theta. Sometimes radians, sometimes degrees as well. Next equation now that we looked at, the next variable that we met was velocity, and we learned that velocity was distance divided by time. It was how fast something was going. So following this same equation, we need something for velocity over here. We're going to get, so distance, we're going to have a theta, and remember that time is just the same. So theta over time, so how fast it's spinning, we're going to call that the Greek letter omega. It looks like a curvy W. Omega is what that one is. Then the natural progression. Next we go to acceleration, and that was our velocity over time. And again, we're going to come over here and we're going to use our rotational velocity. That's what omega is, rotational velocity. And that's going to be divided by time. Remember, time stays the same. So the acceleration turns into angular, this is angular velocity. This is going to be angular acceleration. It's given by the Greek letter alpha. The Greek letter alpha looks like kind of like a fish. The next progression of things here is I would write down all the linear kinematic equations. And then I would translate them over here to our rotational kinematics. But we're going to skip that part because I feel like we've had the physics is essentially the same, and there's nothing really new to learn there. So we're gonna breeze over that. And if you remember, we later on in the game we met another variable, and its name was mass. So mass, does mass have a rotational analog? Does it translate over in rotational land to something else? And well, I wrote it down, so yes it does. Mass is is a indirect measurement of this idea of inertia. So something that's really, really small, something with a little mass, is going to be easy to push. It's going to be easy to get going. But something with a rather large mass is going to be harder to change its velocity. It's going to be harder to get it going. The same thing applies in rotational land, except now instead of pushing things in a linear way, we're going to ask ourselves, what is I? We're going to ask ourselves how hard it is to get something spinning now. So, for example, here's a longboard wheel. We can spin it fairly easily. It has a small, whatever this rotational mass thing is, it's pretty small. Compared to, let's say, we get this spinning, it's pretty easy to stop it. Let's say we want to try and stop the Earth from spinning. Well, that would be a different story. Our rotational analog is represented by the letter I. And the letter I is called the moment of inertia. The moment of inertia. And that's just going to describe how hard is it to get something spinning. How easy is it to get something spinning? Just like mass is, how hard is it to get something moving? How hard is it to get something to stop if it's already moving? So we'll talk about this I a little bit later on as well. The next thing that we learned about was forces. We learned about statics and dynamics. Let me just set this up. So now we have a mass analog, and we can continue on with our talk. So remember, the next place that we went here was to our force unit, and the major equation that we had there was Newton's second law, the granddaddy of all equations. That's F is equal to ma. And when let's translate this over, we know that mass is now going to be our moment of inertia with the letter I, and A was given by our acceleration, our angular acceleration. Well, what is force in the rotational sense of the word? Well, actually, folks, we've already met this one. It's our old friend torque. It's our old friend torque. So when I apply torque on something, I'm going to cause it to accelerate. Just like when I was pushing on the door, I caused it to accelerate. If it was a really, really heavy door, it had a big moment of inertia, then it would have required a lot of torque to get it to accelerate. The next thing we learned about was our energy unit, and we're going to look at something called, well, first let's start. We had our kinetic energy was 1/2 mv squared. Let's go ahead. There's no fancy name for this one. We're just going to call it rotational kinetic energy, and we can translate that one right away. We get 1/2, we have I, and we have our omega squared. And of course we went to momentum not too long ago. Momentum is given by mass times velocity. We can translate this one easily. It goes, the analog for mass was moment of inertia, and velocity was omega. And angular momentum is what it's called. And angular momentum is given by the letter L, angular momentum. Let's briefly talk about these last two here, starting with rotational kinetic energy. So this equation tells us that if we give something a spin here, the amount of energy that is stored in this spinning wheel is given by this wheel's moment of inertia multiplied by the square of how fast it's spinning around, And of course, we have our momentum here given by the angular velocity times its moment of inertia. The larger the moment of inertia, the harder it is to stop it. And something that is That is very cool. There's a very cool demonstration that we'll look at tomorrow dealing with this angular momentum, and it deals with this fact that angular momentum is always going to be conserved. It's always going to be conserved. So if L is always going to be the same, and we change something about the I, then that means something changes about the W, and we'll explore that tomorrow. And that is all that I have for you tonight. I just wanted to introduce you. I wanted to bring you over into rotational land just briefly before we carry on into next units. So tomorrow we'll work with mainly these equations here and explore a little bit more about what they mean.